Okay, so in the last lecture we have discussed two ways to see new particles when they are produced in interactions of other particles. One is to measure total energy in the centrum of mass, and the second one is to measure invariant mass of the set of the particles. Look, we are starting at 11, so please be in time. Discovery of charm particles actually employs both methods. There were two experiments in which charm particles have been discovered, and one is in Brookhaven. The head of this experiment was Ting. And that was in 1974. And what he has studied is the interactions of protons with beryllium target and with final state, which contains a number of hadrons, because this is high energy, relatively high energy experiment, and appearance of E plus E minus pair. So this is fixed target experiment. Protons were accelerated at the energies 28.5 GeVs. So they hit the target. And then among various particles, in some events, not at all, events E plus E minus pair appear. And as we discussed in last lecture, appearance of this pair may actually indicate that this pair appears through decay of some new particle. To establish this, one needs to measure invariant mass of E plus E minus. And let me remind, this is defined as, in this case, energy of electron plus energy of positron squared minus momentum of electron plus momentum of positron, again square, and then we take square root of 2 of this expression. So this is Lorentz invariant, and therefore you can do these measurements in any reference frame. And of course this was a lab frame, and it was not centrum of mass frame, and it was not the centrum of mass frame of E plus E minus. Nevertheless, what we are measuring here is some invariant which may give us measure of the mass of the particle if it is produced. So the idea of the experiment is to measure all these characteristics of E plus and E minus. And let me give you some details, because this is one of the first experiments which uses multiple detectors. This is what is realized to a large extent at LHC experiments. So the setup was the following. Proton beam hits the target, and then it was 2 arms spectrometer. Precisely to measure as small as possible precise way characteristics of electron and positron. So after beryllium target, it was magnet, which actually split electron and positrons into different directions. And along the tracks of the electrons, there were positrons, there were several different detectors. The first is Cherenkov counter, or Cherenkov detector. and it's quite symmetric. It was another Cherenkov detector here. And remember, Cherenkov radiation doesn't take much energy, so the particle just passes through with not big energy loss, but it gives you the cone, and so you will at least see the presence of some particle which actually pass through, and you can measure precisely the direction. Then it was multi-wire chamber. Actually two, and also multi-wire chamber here. Which also measures the tracks, and measuring ionization, you can measure also energy and have some information about momentum. And finally, it was electromagnetic colorimeter, which is even more precise, gives more precise measurements of the energies. So again, the goal of this multiple detector experiment is to measure precisely energies and momentum of electron and positron, and also identify these particles, because some other particles can be produced by zeros, by plus, by minus, and you need to distinguish electron and positron from other particles. So what is the result of the experiment? What was measured is number of events with a given invariant mass. In general, the distribution looks like the background. And of course, the plus and minus can be produced in different ways, and in particular, just electromagnetic interactions of the photon, right? You have here interactions of charged particles, and you have here production of photon, and then photon can produce electron and positron pair. So this is electromagnetic interaction, and typical distribution will be like this. It's falling down because you have more stronger interactions at small energies and small transfer momentum. But on the top of this background, Tink and collaborators saw the peak. Peak, and this is the background. Due to interactions of this time gamma, and here the plus, the minus. With typical 1 over, say, energy or energy square of Q squared dependence, because you have here propagator of gamma, which gives you this 1 over 1 of S more precisely for this process. Okay? So the peak was at double EE 3.1 GeV. Now the width of this peak is another important characteristic, was actually comparable with energy resolution, because in each of these measurements, of course, you have error bars. You have error bars in measurements of momentum of electron, positron, and energies, and also the angles. And therefore, you can see this, the reconstruct W with a certain error bar. And the peak, the width of the peak was comparable with energy resolution. Or reconstruction. Which means that genuine peak, and we will discuss this later, how this, these peaks are formed due to production of new particle is much narrower than this what has been observed. Now, why appearance of particle shows up as the peak? Who knows this? So, you see here the peak. Why this is kind of indication that you have production of particle at this, with this omega, with this W invariant mass?
Resonance?
So, who knows what is the resonance? So we will discuss specifically, but indeed, appearance of the peak indicates that we deal here with production of particle, which then decays. And remember what we were saying last lecture, that if you are sure that E plus and minus appear through decay of a single particle, then omega gives the mass of the particle. Remember our consideration last lecture. So which means that here we deal with the production of particle with mass which equals W E plus E minus peak, and that will be 3.1 GeVs. You will have exercise actually to store the mass using invariant mass of decaying particle. So the interpretation is that we have collisions of proton and beryllium target, which produces for us this particle. And in this experiment it was called J particle, which then decayed to plus and minus. Let me write here J. So this new particle has been identified as called J particle, and then it was set of hadrons usually accompanying the production of this particle. So the particle decays electromagnetically into E plus, E minus. And what I said already, the decay rate of particle is much smaller than observable width of the peak. So this is one experiment.
What was the energy resolution in this experiment?
I don't remember precisely. I think that that was at least say 10 MeVs or things like that. Almost like 100 times bigger than internal width of this part.
So do we know precisely the value of gamma J now?
So then that was computed later.
Yeah, so of what order it is?
So that's let me discuss. Okay, I can write this exactly. So this width is 0.087 plus minus 0.0005 MeVs. But I will say a little bit more about how this has been computed. Now the second experiment was a slug, and it used E plus and minus collider. Remember, slug was this linear collider, and several important discoveries have been done there. So the second is slug experiment, which stands for Stanford Linear Accelerator. So the spokesman of this experiment was Burt Richter. And that was the same year, simultaneously, almost as Brookhaven experiment. And what they measured total cross-section of a plus and minus annihilation. So everything. So the slug accelerator operates in the following way. You have two tubes in which electrons and positrons are accelerated, and then they are injected into storage ring. And then here it was a detector. Actually, storage ring has a name. It's a sphere. And here it was a detector with the name Mark 1. And the detector was composed of spark chambers. And shower counters. So to detect so-called soft component, which is essentially due to electrons and positrons, and spark chambers is good to detect muons, for instance, or ions. I know you discussed how that works. Remember, spark chambers is when you have big tension and the particle crosses, produces ionization, then the discharges just start producing small avalanches, and then you do photos. So, what was the result? So what they measured, dependence of number of events as the function of square root of S. And here, the energies of electron and positron were the same. So essentially, a lap frame coincides with the centrum of mass frame, and square root of S is given by two energies, and this is the energy of electron or positron. So what they have seen is the following: sigma as the function of square root of S. Again, it was a background. But then starting from certain energy, the peak appears of the following form. So it's sharp increase, but then a long tail, this tail. And that beginning of this peak is at 3.1 GeVs. Okay. So what is interpretation? So the appearance of this peak corresponds to, again, production of some new particle. And then remember, as we discussed, if you have annihilation of the set of the particles with production of single particle in final state, then square root of S at which this happens gives the mass of the particle. So that is interpretation that we have particle with some mass which is approximately 3.1 GeVs. So the interpretation is that we have this due to annihilation of E plus, E minus, and this new particle psi, and which then decays with different final states. Now the tail corresponds to the situation when you have E plus, E minus annihilation with emission of gamma. So if you have E plus, E minus, and electron or positron emit gamma, of course you need to have slightly higher energy of electron and positron to produce a given psi. And that tail corresponds to such a process where, apart from this new particle, you produce also photon. Okay, with the tail. Now they of course observed different events, final events, and in one of these events they saw something like that. I will show you slides. Something like that, where this corresponds to positron. This is one of the final events. It pi minus, and here is pi plus. And so that event gives the name of this particle. We call this psi. So after this, it was clear that this psi particle is essentially the same as it has been observed at Brookhaven, and therefore the name of this particle, it has double name, right, J psi. So what we deal here with this particle with the name J psi. It was by far not trivial to understand what is the property, what is this nature of this particle. That was hadron. It was more or less clear because it was produced quite copiously in Brookhaven in strong interactions, so it has this electromagnetic decay. And actually, even Mayani, who was one of the guys who worked on the charm particles, has written paper on interpretation of these events which differ from charmonium, what we know now. So it was quite non-obvious, and only after studies of properties of this new particle, it was concluded that that corresponds to a composite state made of charm and anti-charm quark. So it was a set of the experiments, and those experiments are also continued. And what has been established, that this particle, again, is J psi, is hadron, so it has strong interaction. It has mass, so more precise, 6.81, maybe now it's even more precise, MeVs, which means that this is 3 GeVs, 3.1 GeVs. The gamma I have already written. So gamma is 0.087 plus minus 0.005 MeVs, which is much smaller than the mass of the particle, but that corresponds to very narrow resonance, in fact. And the gamma over m is here 3 10 to the minus 5. So the interpretation was that J psi is a composite state made of charm anti-charm quarks. And charm quark has been introduced before. And in 1917 it was used to explain K to small branching ratio of decay of K meson into mu plus mu minus. So that particle has spin 1. We use notations for the particles like spin. It had negative parity and negative C parity. I will discuss this later. So it's composite state of charm and anti-charm quark. However, the total charm of J psi is 0, right? Because we have charm and anti-charm quark, and therefore the total charm is 0. So we are saying that this particle has a hidden charm. And probably I should say even before that, as in the case of strange quark, we introduced a new quantum number. Which is charm, right? In the same way as we introduced strangeness for strange quark. And now every new discovery of quark is associated with introduction of new quantum number. Mass of the quark, of C quark, is about 1.2, 1.3 GeVs. It's nearly half of the mass of J psi, and also this means that part of the mass of J psi is due to interactions. So it is composed of the mass of the constituent quarks plus the energy of interactions between these quarks. That's what gives an observable mass of J-psi particle.
How do you find experimentally the hypercharge or the parity?
Oh, so let me discuss this later, because we will discuss parity and C parity later. So I just made this notation. Spin has been discovered and then parity has been identified. So let me discuss this later.
Okay.
So adding 4 quarks means that now we deal with SU4 flavor symmetry. So in this sense, let me say, it's similar to what we have for spin 1 is like photon, right? It has spin 1. And actually for diagram of decay is like this. You have charm, anti-charm annihilation into gamma, which produces a plus and minus. And of course you have here strong interactions between charm and anti-charm. So remember we had SU3 flavor symmetry before, which includes U, D quark, and strange quark. Now we add another quark. And so the fundamental representation of flavor group is 4, and this is SU4, so the extended flavor group. Let me put here flavor index, so flavor group. Let me say a few words about charm spectroscopy. So once you introduced a new quark, you can compose many composite states using this quark and also other quarks, and that will give you new families, new hadrons. So let me say a few words about charm spectroscopy. So we have mesons with charm quark, charm, and we connect this with U, D, and S. And the same charm we can connect with U bar, D bar, and S bar. So we can have these composite states.
You mean forming a meson?
They form mesons, yeah. You have, and so here we have charm and usual quark, and here we have anti-charm and quark. So that's what we have. And also we can introduce the state with charm, anti-charm, and in contrast with J-psi, these are mesons with spin 0. So these are scalars. Okay. Now, what are these particles? What are these mesons? We have D plus. So these particles called particles with spin 0 called D mesons. So we have D plus, which is composed of charm D bar, D0, which is charm and U quark, and they form isospin doublet, because here we have D and U. This gives you the doublet. So charm is the same quark in both components, and they differ by type of usual quark, by isospin of usual quark. Similarly, we have pair of D bar 0. It's similar to strange quark or K mesons, D minus, and this composed of charm U and this charm bar D. So they form also isospin doublets. So these are two isospin doublets analogous to K meson doublets, but here instead of S quark we have charm quark. We can also compose the states with strange quark, and the name is DS, and the composition is charm S bar. They have also D bar S, char bar S. So those are singlets of isospin singlets because they do not contain D and U quarks. And we have also this eta meson, eta C, which is composed of charm and charm bar. Again, eta C differs from J psi by spin. So what's interesting, the first particle which has been discovered was this charm anti-charm, although its mass is bigger than the masses of these particles. So let us count how many new components we have. So it's 4 here and 3, 7 new mesons are introduced, right? So if we add these 7 mesons to our already known 8 meson family, octet of pions and K mesons, so we have our old octet, which contains pions, K mesons, and eta. And we add 7 new mesons, which you see here. So we get 15, right? So now we have 15 pleth of pseudoscalar mesons. So they have the same characteristics as pion and K, but the difference is, of course, the quark content and masses. And as you know, probably, that 15 is a joint representation of SU4 group. Like octet, so 8 is a joint representation of SU3, and now we have this extension, and now the multiplets have more components, 15. So this is a joint representation of SU4. And the story is the same. What is the meaning of this composition of families? One is classification, so we have this classification. Now we introduce another quantum number, so strangeness, and now we have charm. And so our group has 3 diagonal generators, which can be identified with physical quantities of now charm, strangeness, and isospin. And the sense is that strong interactions are invariant under these SU4 transformations. So this is the whole idea. Not only classification, but also the idea that strong interactions are the same for all these particles. So Hamiltonian or Lagrangian of strong interactions should be invariant under transformations SU4 now transformations. Okay. Of course, the symmetry is not exact because the masses of particles now within these multiplets differ quite strongly. So apart from these pseudoscalar mesons, vector mesons have been discovered. So, and the family of vector mesons also have been recovered, and they have notation D star. So D star is vector meson with charm quark. So the same kind of assignment, however, this quark, charm, and usual quarks are in the state with spin 1. And also baryons with charm quark have been discovered. And for instance, lambda C has been discovered. And it has content like charm U, D, for instance, or charm D, D, R, like that.
The conclusion that the strong interactions must be invariant in these transformations comes from the universality of weak interaction, or what? How?
No. So now we deal with strong interactions. Okay. So which means that Hamiltonian of strong interactions should be invariant, as we discussed before. This is the same like we did isospin transformations. Hamiltonian is invariant, and here is invariance with respect to this SU4 transformations, which means that if you put all these particles in a column with 15 components, and then you have this matrices 15 by 15, you do transformation, and then Hamiltonian is invariant out of this transformation. It doesn't change the form.
But how do they know that from these particles? How do they know that the internal structure is the same, that the interaction is the same for all of these particles?
Well, so first of all, that was hypothesis, right?
Oh, okay.
But then it was checked by in the experiments, because people studied the interactions of these new particles, their production, and and it was established that up to effects of violation of the symmetry due to masses, because in the limit of exact symmetry, you expect that all particles in the same multiplet have the same masses. And here is not the case. Actually, the masses is now is 1.8 GeVs or something like that. So I will give you some precise even now. So let me. I think I had somewhere. So the masses is masses of D mesons are approximately 1.8 GeVs. Remember, masses of K mesons were around 0.5 GeVs, 490, 480 MeVs, and here is much heavier. So what is important, that this is quite strong breaking of the symmetry, and even more important that it is much bigger, this mass, than the QCD scale, the scale of strong interactions. So I mentioned a little bit, but we will discuss the scale of QCD. And therefore, the presence of so big mass, of course, influences strongly the probabilities. It's not like you simply have the same probabilities, like for instance in the case of isospin, which is very good symmetry. It's weakly broken, and the weak breaking of SU2 is because the masses of U and D quark are very small. They are much smaller than this QCD scale, which is something like 300 MeVs. So let me discuss a little bit the case of D mesons. The story is the same as with charm, with strange particles, or the meson case. So what we are assuming and what has been confirmed is that charm is conserved in strong interactions and in electromagnetic interactions. Like in the case of strangeness, but charm is broken in weak interactions. Again, like in the case of strangeness. Now, D mesons are the lightest particles which contain charm. And therefore they can decay only in particles which have no charm, and therefore they can decay only due to weak interactions. So the consequence is that D decay due to weak interactions, although they are strongly interacting particles. And some examples of these decays are the following. D plus can go to K0 bar, L plus, and new one. Actually, one of the exercises will be to draw the diagrams which correspond to these decays, or D0 can decay into K minus, L plus, and neutrino. The lifetime of these decays, lifetime of d meson essentially, is 10 to the minus 12 seconds, which is typical for weak interactions for these masses. Remember, for pi we had decay rate something like 10 to the minus 8 seconds. Here is lifetime 10 to the minus 8 seconds. Here's 10 to the minus 12, but the difference is mostly because difference of the masses. And you remember that, say, three-body decay is actually rate of this decay is proportional to the energy release in the fifth power, so that produces so big difference in the lifetime. But still, it's not 10 to the minus 20, typical for strong interactions. So again, you will have exercise to draw the diagram how these processes occur. By the way, you see here not only charm is violated, but also strangeness is violated. Right? We have K mesons in the final state. Charm has been introduced in the same doublet with combination of S and D quarks, which is orthogonal to what is staying with U quark. So you have cosine theta, then S quark minus sine theta D quark. I denoted this as cosine theta, and this is Habiba angle, cosine of Habiba angle. So the current is proportional to cosine and sine. So here, charm mostly decays into S because cosine is bigger than S. And now we have Habiba suppression of the transition of charm to D. So this is Habiba suppression, Habiba suppressed transition. Habiba angle suppressed. So charm likes strangeness, so to say, because it likes more to have transition to strangeness. Easy to remember, right? Questions?
Is there a historical reason to why it was called charm?
I think that was called, frankly, I don't know. You know, the people are discussing strangeness, charm, and beauty, things like that. I even don't know precisely who it is. So the C quark, this fourth quark, was introduced by Bjork and Glesher, and I think probably Glesher gave this name. I don't know precisely. But you see, these are our notions, right? So this object doesn't know that he's, charmed, and another one doesn't know that he's strange. It's our kind of image of the world, right?
It was strange it was strange at the beginning.
Well, strangeness is clear, and strange was strange because of this way how it was produced and decaying. But the charm origin, I don't know exactly. Maybe in some books it's beauty. Top has no kind of special name, top quark.
Up and down?
Well, up and down also. Now we will move to another discovery. And we will discuss discovery of tau lepton. By the way, later we will discuss with beauty, particles with beauty, and you will see that the story is quite similar. tau lepton. So tau lepton has been discovered in 1975. So you see, in several years, there were a number of discoveries. This is kind of the era of big discoveries, but nowadays, not many discoveries of new particles. It's actually none. By a group of the researchers, this spokesman, Earl, and he was working at SLAC, so using the same SLAC E plus E minus accelerator. And he studied final states in E plus E minus annihilation. So that's type of the processes. And he studied the events which appear at different energies of the beams, which means different square root of S total energies in the centrum of mass. And among many different events, the collaboration observed events of this type: E plus E minus go to mu plus E plus nothing. And nothing means something which takes the energy and momentum, but it is not observable. So they observe events when you have mu plus and E minus, or mu minus and E plus. So let me put here plus, minus, minus, plus. They also observe events when you have mu plus, mu minus, and E plus, E minus. This is not surprising, so you expect appearance of such an events, but this is strange. It is strange because apparently you have violation of lepton number. So what are the properties? So both LE and L mu are violated in these processes.
Why not including neutrinos?
So we will do this. I mean, what has been observed. Otherwise, you have also mu plus, mu minus.
But
So what you see is a violation of lepton number. Let me put for observable particles. That distinguishes this type of events when you have mu plus, plus mu minus, plus something. The second important feature is that these events have threshold. This means that such an events appear only above certain energy. So they appear when two energies of E plus and minus, which is square root of S, becomes bigger than 3.6 GeVs. So below this energy, these events are not seen, and they appear when the energy becomes bigger than 3.6 GeVs. So of course another property, point one, is that we have energy and momentum loss. So the energies of muon and electron, the sum of these energies is smaller than square root of S in the collisions. Now the distribution of energies of muon and electron is continuous. It's not like you have in each event the same energy of muon and electron, so that the energies and momenta of electron and muon varied from event to event. And so to say the energy and energy spectrum of electron and muon were continuous. So this energy spectrum were continuous. In different events you have different energy. So spectra are continuous. And finally, number of events when you have different charge assignment, it was the same. So number of events when you have mu plus and E minus was equal to number of events when you have mu minus and E plus. So you have these observations, and now let us consider what is interpretation of these events. I'm asking this every year, and it's interesting that in very rare cases, I think it was 1 or 2 cases when probably people knew how to give interpretation of this event. So how these events were produced? Suppose you are experimentalist and you observe this type of events with these properties. So how you would interpret this? Have E plus and E minus in initial state. Then what? How you would get this final state with these properties?
The fourth thing tells us that there is something else apart from these two particles in the final state with the continuous spectrum. The muon.
Which particles?
Well, that we can think about, but we do know that there has to be something else apart from these two particles in the final state.
So again, this is beginning, right? And then something happens, and I have say E plus and mu minus, and maybe something else. So this is what I see, and then I want to have interpretation of this event. So how I should connect this? So this is very typical analysis of some. You see something new, right? Something new. Now you want to give interpretation, and you see information is written here is enough to give at least the simplest explanation. So this E plus and P minus come from decay of single particle or several particles. So it's single, right? So you have this connection. You want to have something like this, right? So this new particle doesn't conserve electron numbers, right? So this is what you want to do. Now, and how to connect with the plus and minus? And so what to do with this missing energy and momentum, why it is. So how you, one neutrino, how many neutrinos you would have? 2 neutrinos, okay, 2 neutrinos. Okay, neutrino and antineutrino, right? So for instance, neutrino and neutrino, antineutrino, I don't know where it is. Now how to connect this?
Okay, because we know that if you had an electron and positron in the initial state, then they are either to form a photon.
So you want to have this annihilation into photon.
And probably then this photon decays into one lepton and one anti-lepton.
Lepton decays.
No, the photon.
Photon decays.
It gives you a lepton anti-lepton pair, but we don't know that lepton and anti-lepton probably. It's a new lepton probably.
So gamma is transformed to what? What is here?
Some electron and anti-electron. We don't know about those electrons.
Okay, so
And
let me put this as tau.
okay.
And then how tau is?
Then tau 1 decays into a positron and the electron neutrino and probably then tau neutrino. And then tau minus decays into mu minus and mu neutrino and anti-tau neutrino.
Okay, you knew this or?
Yeah, I mean, because I read about Martinez.
Yeah, so you see, okay, and it should be like this, and then there. This is mu tau, and this is positron. So if it is tau plus, and here is mu e, and so this guy will decay into. New tau, that should be bar. And here we will have this tau minus, mu minus, and mu. So this because you knew, but I remember that once we were discussing this during half an hour at least. There were different ideas. You see, then how to explain all these properties? You see, we have visible violation of Lepton number. We do not see neutrinos, so you see mu minus and a plus. And of course, you will have also decays when you have also muon here, mu plus and neutrino. Then, if the mass of tau is 1/2 of the threshold, which is 3.6 GeVs, we will have 1.8 GeV. So that the mass of this particle is around 1.8 GeVs, and therefore you can explain the threshold that these events will appear when the energy available is bigger than 2 masses of this particle. So that explains the threshold. The energy loss is due to neutrinos, and then the continuous spectrum of electrons as positrons are also due to neutrinos, because decay of tau plus. In the case of tau plus, you share the energy between neutrinos and electron, positron, and muon. Okay, so all the properties of these events are explained in such a way. So questions?
Were you not able to detect these neutrinos in the experiment?
Sorry?
Were you not able to detect these neutrinos in the experiment?
Well, number of events here was I think something like in the first experiment around 50 or so, or even less, maybe 30 events of this type, and it's just too little events. You cannot. Even now we have only now started to discuss a possibility to detect neutrinos from, say, decay of heavy particles. Just number of events is too small. Okay? So what has been established, not immediately, by the way, and you see, when even drawing this picture, you may ask different questions. What is the spin of this new particle, tau? Depending on spin, you may have different modes of the decay, and you need really to check everything. So what was eventually established is that the spin of tau is 1/2. So it was confirmed that we deal with something which is quite similar to what we had before. In the interaction here is current times current, right? So this kind of similar to muon decay when you have here you had before muon, which it transformed into muon neutrino, and then you have this electronic pair. So it's after some measurements, it was established that spin is 1/2, and you have decay similar to what you have in the case of muon decay. Now the mass, more precise measurement, is 1.777 GeVs. The lifetime of tau lepton is 4.6 times 10 to the minus 13 seconds, which is typical for big decays of objects with this mass. And this is three-body decay. Again, you have some exercise. Now, from this, we have a number of important applications. So we discovered the third lepton family, third charged lepton. And we can guess that there is another neutrino which corresponds to this tau lepton. By the way, tau neutrino has been discovered in the year 2000. You see, it took 25 years when really tau neutrino has been discovered. Here we can assume that maybe this is not new neutrino, but new E or new mu, and some combination of new E and new mu. But people didn't doubt much about this. It's most probably that nature really has this way to have doublets of the fermions. Leptons appear as in their currents as charged lepton, and then corresponding neutrino, which differs from other neutrino species. But again, that has been explicitly shown later. So then again, so this is doublet. New doublet of leptons with new neutrino, and then new tau is not new E and new mu. So now the interactions are in the form of current, and one can guess that it is again V minus A current, and that again has been checked. So this current, which is responsible for the transitions you see, and of course there is conjugate current. So now we can introduce new lepton number. L tau. And to say that this L tau is actually conserved in all the interactions, strong electromagnetic and the weak interactions of the type we are discussing now. So these lepton numbers are violated, as we will see now, by masses of the particles, and masses are due to Higgs mechanism. So it means that these lepton numbers are violated, but due to these Yukawa interactions. So this lepton number is described in such a way that tau and nu tau have lepton number 1, and all other lepton numbers, electron and mu, for these particles are 0. So let me probably write this ones. Tau, L tau, tau equals L tau, nu tau is 1. For antiparticles it's -1, and Le and L mu are zeros for these particles. And for electron and muon, vice versa, L tau is 0, but L mu or L E are non-zero. And it seems that it is conserved in all weak interactions. Finally, since we have here now the third family of leptons, according to quark-lepton symmetry, we can expect that there is a third generation of quarks. Actually, that was one of the first confirmation that the third generation of quarks existed. Although a possibility of existence of a third generation of quarks was hypothesized a year before by Kobayashi and Masukawa in connection to explanation of CP violation. And I will discuss this, I think, next. Questions?
Can you observe a process in which this tau minus particle decayed into E minus and electron neutrino instead of muon neutrino.
What you want to have tau, of course, here you may have E minus and neutrino, electron neutrino, electron antineutrino, and here you may have, of course, mu plus and mu. This is your question?
No,
yeah, of course.
The upper one should remain unchanged, but the lower one is just electron. So you get a positron and an electron.
Oh yeah, sure. Yeah, I said that also there are events when you have here also yeah, so like this. So all the combination, all four combinations of.
You also mentioned that the case with anti-muon and electron have the same number of this, but due to mass difference, is there not a preference in?
Well, you see, the mass of the muon is 0.1 GeV, which is, say, almost 20 times smaller than the mass of tau lambda. Of course, there is some difference, but it's not a big difference. The corrections are quite small. It's not like you have preference by factor of 2. Maybe just less than 10% about what I expect. You can do the computations. Some more questions?
Why was tau neutrino difficult to discover?
Oh, you need to create intensive beam of tau neutrinos. You know, the situation is easy, for instance, with muon neutrinos, because muon neutrinos are produced by production of pions. Copies produced in strong interactions, and that gives you a muon neutrino beam. For electrons is also easy, because K mesons produce electron, if you want, or beta decays, and in reactor experiments you have big fluxes of electron neutrinos. For tau neutrinos is very difficult. I will discuss a little bit this. So what is interesting that you produce tau neutrino in the decay of ds mesons. So you first produce charm mesons, and then these ds mesons decay with emission of tau. Then tau and tau neutrino, then tau decays.
So do we have tau neutrinos in cosmic rays?
Of course, yeah. But we also produce copies with these neutrinos due to oscillations. So you have atmospheric neutrinos, and originally they produce fluxes of muon neutrino and electron neutrino. Then muon neutrino flux oscillates in tau neutrino, and for instance in super-Kamiokande the fluxes of atmospheric neutrino, tau neutrino, and muon neutrino, they are all the same order. Through oscillations. Okay? Now, before I will discuss discovery of B mesons or discovery of B quark, let me give you some theoretical introduction. So, to some extent, existence of B quark was not immediately predicted from the experiment, but it was, B quark was introduced, and third generation of quarks has been introduced in attempt to explain CP violation. CP violation will be discussed in one of the final lectures, and now I will give just a short introduction to this. CP violation. And third generation of quarks. So we discussed weak currents, and weak currents have V minus A structure. Again, I will discuss parity violation later. So which means that weak currents violate parity, violate parity. That is symmetry between left and right. So you do reflection of coordinates that change x to minus x or z to minus z, and you will get something which differs. So you have no symmetry between this type of reflection. So V minus A structure violate parity, the symmetry between left-right. Not only this, V minus A violate C symmetry or C conjugation. So you can conjugate your particles, and everything is fine when you consider electromagnetic interactions or strong interactions. But this V minus A breaks also symmetry between particles and antiparticles. And this is also a consequence from V minus A. However, this V minus A structure conserves C and P. So if you do transformation, say first C transformation and then P transformation, then this your Hamiltonian of weak interaction is invariant. Again, you will have exercise to check this. Or you can first do P transformation and C transformation. So these combined transformations left the Hamiltonian invariant. This is V minus A Hamiltonian, which we have discussed before. So, and for a long time, actually not very long, but say 10 years, people thought that the CP is good symmetry. So parity is violated, C is violated, but CP is good symmetry. But then in '64, Cronin and his group have discovered CP violation. So even CP is violated. So that has been discovered in K meson decays, and we'll have lecture about this. And then people start to think how to explain this CP violation in the theory. There were a number of solutions proposed. One of the first actually was the solution proposed by Kobayashi and Moscova. And that was in 1973. I said got Nobel Prize for this. And the idea was that the origin of CP violation is just complexity of some coupling constants or interaction coupling constants in Hamiltonian. Simple, right? And more precisely, what they are saying that the mixing parameters which we have introduced, and we introduced Habib angle, actually is not just a single real parameter, but you can introduce a complex parameter. So let me explain this. And complexity of mixing parameters is actually the origin of CP violation. So suppose we have Lagrangian, which has the form lambda, with some coupling constant, and operator, which is made of operators of particles. It can be product of 4 particles. Like in our Hamiltonian, we have 4 fermionic interactions, right? So, but it's in general, so you have this. Plus you have Hermitian conjugate, which is a lambda conjugate, and here is Dagger. You may have many operators of different type, but this is kind of generic feature which I want to illustrate using this simple case. So this is coupling constant. And this is operator. made of operators of fields involved in the interactions. Now, what CP transformation is doing? So you do CP transformation of fields which are inside these operators. So under CP, O go to dagger, and dagger go to O. And therefore, under CP transformations, our Lagrangian is transformed to lambda CP, which is lambda O dagger plus lambda star O. Right? I just substitute here, put here O, and here is O dagger. And Lagrangian is different because here you see lambda is staying with just O, and here is lambda is staying with O dagger. But they will be the same, so you will have invariance that lambda equals lambda CP transformed if lambda is real. Okay? So if lambda is real, then I have no conjugate here, right? So I will have the same Hamiltonian. So which means that if you have some coupling constants, which are imaginary, have imaginary parts, then potentially you have CP violation. It's not sufficient, but this is kind of necessary condition to have this CP violation. Okay? So what Kobayashi and Masukawa suggested, precisely that you have some couplings in your Lagrangian which are complex numbers, and they suggested that these are mixing parameters. So mixing parameters are complex. So people invented other possible mechanisms of CP violation. For instance, some vacuum expectations of the fields, although we haven't discussed, can be complex, which means low energy states of your fields can be complex, and that can be also origin of CP violation. But after all, after many years of different studies, the source of the CP violation was indeed identified as a complexity of the mixing parameters. So after that, Kobayashi and Masukawa got a Nobel Prize. So let me discuss this mixing, which can be complex. And let me introduce mixing matrix first. So we introduce quark current, let me remind you, as U gamma alpha 1 minus gamma 5 d theta plus, after introduction of charm, gamma alpha 1 minus gamma 5 s theta. D theta and s theta are orthogonal combinations of s and d quarks. So let us introduce column with up quarks, UC. So these are quarks with electric charge to third, and column with down quarks, as charge is minus 1/3, which is d and s. The charge is minus 1/3. And then in terms of U and D, I can write this current as U column gamma alpha 1 minus gamma 5 V C and D, where we C equals cosine theta sine theta minus sine theta cosine theta. Do you see this or no?
Yeah.
So
That notation is dangerous.
yeah, so this is what people are using. So what is dangerous for you? Tell me.
Because you have S theta and S theta.
Yeah,
Meaning
so
different things, in this case a field and the other.
that's standard. I can write if you want cosine,
Okay,
but
that's
nothing,
fine.
but nothing more. So these are this cosine theta Kabibo. This is cosine theta Kabibo. This is sine theta Kabibo. Okay? Do we agree? And let me write just one, so that, for instance, this S theta is again cosine theta Kabibo multiplied by S minus sine theta Kabibo multiplied by D. So that has been established in the experiment, right? So these are mixtures of quarks. And these are just identically have written this not as sum of these two terms, but in terms of this matrix. So if you just open this, you have here column, U, see? Then here you have matrix with this cosine, sine, and here you have D and S, and if you multiply this, you will get to this expression. Okay? You can check this by yourself. So this is what is called mixing matrix. So what mixing matrix is giving to us, it connects mass states of down quarks with mass states of up quarks in charge currents. Now it was questioned, for instance, why we put mixing on down quarks, why not to up quarks? So this is more kind of symmetric. I can put this matrix here, and it's clear to attach this mixing to upper quarks, not to down quarks. So what is again important? That mixing is relative. It's relative between mass states here and mass states here. So it connects the states in charge current. Right? Agree? Now, so we introduced this cosine and sine, but in general you can ask why we put here real parameters. So in general we can add phases in this expression, and in general this mixing matrix can be written as cosine theta I phi 1 1. Here is sine theta f 1 2. Here is minus sine theta phi 2 1, and here cosine theta I phi 2 2. Right? So in general I can introduce these complex phases. Who told us that this doesn't exist? Now the matrix should be unitary. And it should be unitary because we want to have a connection between correctly normalized states. So we normalize U and D, so this big U and D in such a way, in just a usual way, right? So that U bar is 1, right? So we do this normalization, and therefore this matrix should be unitary, which means that we see dagger times we see is unit matrix. So this is unitarity of the matrix. You don't want to change normalization. By the way, let me just make this comment. Maybe it's not important for the time being, so we can call this combination as D prime. So that its D prime has this column with D primes has definite weak interaction properties, right? And we discussed mixing also the one which connects D prime, can introduce S, B, C, D. And so this is a mixing, and mixing then connects mass states with the states which have definite weak interactions, which enter with a certain upper quarks in charge currents. So this is the same interpretation. You just can stop at this point without introducing D prime. However, you can introduce also D prime. And so D prime are the states which have definite weak interactions because they enter in diagonal way with U and charge quarks. And the essence of mixing that it connects states with different properties. Mass states with flavor states. Now, what unitarity gives to us? Unitarity gives, in this case, one condition. So if you insert this matrix, and to have this unitarity, so that actually gives you 4 conditions, right? Because you have matrix 2 by 2, and this is unit matrix, and then you need to do the things. And then to have this unitarity, and you will check this, you need to have F12 equals minus F21. So it gives one condition. In this case, unitarity imposes one condition, which tells us that these two phases should have opposite sign. So this is what unitarity gives. Another thing, and let me maybe take 2 minutes, which is important, is so-called rephasing. What is this? You see, what has a physical meaning is that you can attach an arbitrary phase to your fields, because eventually what you compute the probabilities. These are our observables, and they compute moduli square of expressions for amplitudes, and therefore you can always take some field and then make transformation to of this type, adding the phase. And this phase has no physical meaning, because eventually you compute moduli square, and you compute moduli square of wave functions, and therefore this phase disappears. The problem which we are trying to discuss is the following. So you have 3 phases left after this applying of unitarity. But you see, not all these phases may have physical meaning, because they can be absorbed when you calculate moduli square. In particular, if you can eliminate these phases by doing rephasing of the fields, then these phases have no physical meaning, and therefore you cannot explain observable CP violation effect. So, what is the freedom for this rephasing? We have 4 fields involved here, right? So we have U, charm, D, and S fields. So we can introduce 4 phases, doing rephasing of 4 fields. So we have 4 fields, and we have freedom to remove complexity from our theory, doing rephasing. So this is rephasing. So we have 4 fields, 4 phases. However, one phase can be excluded, because if you do rephasing of all the fields by the same phase, it doesn't produce any effect eventually, right? So which means that you have 4 phases minus 1, so you have 3 phases, which you can use to eliminate complexity in your Lagrangian. Right? So imagine that you look at this expression, for instance. If you add the same phase to D, to S, to U, and to C, this phase just cancel, right? Because you have conjugate here and no conjugate here. So what has actually some effect is difference of the phases between different fields. So that may have effect. So bottom line is that you have 3 phases available to do rephasing. And we started with 4 phases. 1 is eliminated by unitarity, and 3 phases can be eliminated by rephasing of the fields. Which means that nothing is left. Which means that in the case of 2 generations, you cannot introduce complex phases which have physical meaning. Which means that in the case of 2 generations, you cannot explain CP violation effect by introducing complexity in the mixing parameters. Then what Kobayashi and Maskawa thought that maybe if we have 3 generations, we will not eliminate all the phases in this fashion. And in fact, when you go to higher dimensions, so bigger number of generations, you will have more phases to start with, because in the case of 2 generations, we have 2 square, right? 4 we have phases. So if you have n generations, then the number of phases you start with is n squared. And the number of rephasing freedoms increases as 2 times n, because you have, say, 2n field. And so this is kind of the idea which cost Nobel Prize, you know. It's just the number of phases which you can eliminate increases slower than the number of phases you start with. So you will have exercise to show. You can do this, right? So what's the problem? So we stop at this point. We continue more. Right?